start now. This is the theorem. We're considering this theorem. Before that, some multivariable function available in the Google website. Multivariable function. These are some multivariable function. Shape will be the variable function. Okay, x-axis is there, y-axis is there, z-axis is there, and then there is a specified shape for the function. These are all multivariable functions. Okay, so think such a context in your mind when we discuss multivariable functions and theorems. Okay, this is the examples of multivariable functions. You can search in Google and you will get a number of examples. So the theorem is f from D to R. D is the domain and R is the real valued function, continuous function, defined on the closed bounded such D subset of R raised to n. And there exist points P and Q in D such that f of P equal to supremum of f of x and f of Q equal to infimum of f of x. So remember that the domain is closed and bounded. You have to remember that the domain is closed and bounded. Then only there exists point P and Q inside, such that f of P equal to supremum of f of x and f of Q equal to infimum of f of x. Similarly, this is in the case of multivariable functions. Similar results can be, I think you have studied similar results in your degree classes. This is the book of Bartle, and in this book you can see that maximum and minimum, and these are the maximum minimum theorem. Okay. There exists, that means we have to prove that there exists a point S star and S star such that S star equal f of x star equal to supremum. Similarly, some other y star in such a way that the f of y star equal to infimum. So similar theorem is proved in the multivariate case. That is we are discussing here. Okay. So yeah, this is the multivariable version of that theorem I have shown in the book of Bartle. So let us move to the proof of the theorem. Okay, I think you have sufficient knowledge in univariate real analysis based on your theory classes. If you have a good thorough understanding in real analysis, if you don't have such a thorough understanding, you have to read the book of Bartle and understand the concept again and again. Then you can follow this process, because this is mathematical, only mathematical. There is no statistical content. But we applications of these theorems in statistics. Understanding we will use method contradiction. What is that result? We should do that. We should contradiction. There is a procedure. Suppose that f of x is not bounded in D. That means we have f of x is bounded. And suppose we are assuming that f of x is not bounded. So if a function is not bounded, what happens? Then there exist some points in such a way that mod f of x greater than or equal to I. So here we can find a sequence of points, sequence pi. This is multivariable sequence pi, I going from 1 to infinity. That is taken from domain D in such a way that mod f of pi greater than or equal to I. If f is bounded, it should be less than or equal to I. Since it is not bounded, there exist some points. So in particular, we select a sequence of points in such a way that mod f of pi greater than or equal to I for I greater than or equal to 1. So that is the first step in our analysis. So this is the reason for calling this topic as real analysis. This is analysis. Okay. Hence, what is the meaning of mod f of x greater than or equal to I? As I go to infinity, then bigger term will also go to infinity. So mod f of pi tends to infinity as I tends to infinity. Okay. Because mod f of pi appears after I. So if I go to infinity, then surely mod f of pi should go to infinity. Since the terms in the sequence are elements in the bounded set, we assume that D is bounded, closed and bounded. We assume that D is closed and bounded. And we take it as D is closed and bounded. And we assume that F is not bounded. So, since the domain is bounded, then the elements or the real numbers, sequence pi will be in that D, and that should be bounded. So that sequence must be a bounded sequence. Okay, we are selecting. Should draw figure. We are selecting a bounded sequence. So we are selecting a sequence, but the sequence belongs to actually in a, suppose this is a D. Okay, this is D. Okay, and we are selecting X, sorry, E1 comma E2 comma etc. belongs to this D. Since D is bounded, what is the specialty of D? Bounded and closed. So since D is bounded, sure, definitely P1, P2, etc. will be bounded. Okay, so that is the idea. You know that in real analysis, we can see that every bounded sequence has a convergent subsequence. We can, in the book of Bartle, you can see that theorem. For every bounded sequence, it has a convergent subsequence. Somewhere in this book, there is a theorem that every bounded sequence has a convergent subsequence. Let it be pki, I from 1 to infinity. Okay. every bounded sequence has a, we used that concept, we used that result that every bounded sequence has a convergent subsequence. So since sequence Pi is bounded, it must have subsequence in such a way that the subsequence is convergent. Okay, if the subsequence is convergent, what happens? It will converge to a particular point. It will converge to a specific point. So let it be denoted as P naught. Let P naught be the limit of this subsequence. Since sequence PI is included in this domain D, which is bounded and closed, there is the converging point will also belongs to this domain D, because D is closed. When D is closed, the limit also belongs to that set. The D has the property that D is closed set. D is a closed set. So every convergent sequence in that set will have the limit in which the limits also belongs to that set D. Okay, that is it. So P naught is, if P naught is the limit of the subsequence, which is also a limit point of D, and hence it belongs to D. Okay, the reason is D is closed. Okay, so we have, I told you we have three information regarding D. D is bounded and closed. What is the information regarding F? F is continuous. Okay. The third information is D is bounded and closed. F is continuous. We will. What is the continuity property? As x goes to C, then f of x goes to f of t. That is the continuity property. Is it right? As x goes to C, f of x also goes to C. That is the continuity property. So here we have proved that. What we have proved that? Yeah, this is P1, P2, etc. Pn goes to P naught. Then we should have, what is that? F of Pi. Okay, f of Pi goes to f of P naught. So we should have f of Pi goes to f of P naught. In particular, modulus of f of Pi, that is a function of continuous function. So in particular, modulus of, what is that? F of Pi goes to we obtain that result. On the other hand, mod f of Pki, yeah, it is the, we are using the subsequence. So f of what is that? F of Pki goes to f of P naught as I tends to infinity. Okay. So by the continuity of f of x. So we have used the continuity assumption of f to prove that result. So okay. On the other hand, mod f of, but we from the beginning we have assumed that mod f of Pi tends to infinity. In the first line you can see that mod f of Pi tends to infinity as I tends to infinity. So definitely the subsequence also diverges to infinity. Okay. So because entire sequence goes to infinity, so definitely from the beginning assumption we should have mod f of Pki goes to infinity. So simultaneously we got two results. What is that? Mod f of Pki goes to mod f of P naught. Okay. Again, we obtain that mod f of Pk goes to infinity. Okay. So what is that? What happens? Simultaneously we are getting two results. So this is a contradiction. This is a contradiction, so that f of x must be a f of x must be a bounded set in D. Okay. So from the assumption we obtained that mod f of Pk goes to infinity. From the continuity assumption we got that mod f of x, f of Pki goes to f of P naught. Okay. So what is that? Simultaneously, we are getting two results, two convergence based on two assumptions or two informations. So if the result was true, we should have the same result. So this is a contradiction. So it shows that f of x must be a bounded sequence in D. Consequently, the infimum and supremum f of x in D are finite. If it is bounded, from the book of Bartle, you can have plenty of theorems like boundedness theorem. Show you. Yeah, this is a maximum minimum exists. And in that case, maximum minimum theorem. What is the maximum minimum theorem? If equal to bounded integral and f continuous, then f has absolute maximum and absolute minimum. Okay, then other theorem. Let I be closed to bounded interval, and f from I to R is continuous on I, then the set f of I is closed bounded interval. So again, that means again we have boundedness property of f of x. That is, since it is bounded, it should have infimum and supremum. So that will be belong to a bounded set, and since it is bounded, it is finite. Okay. Now we consider that we have to show that this equality, what is that, of p equal to p is the point in such a way that f of p equal to supremum f of x belongs to D, or q is the point such that f of q equal to infimum f of x, x belongs to D. So we have to identify such a points. So we assume that that does not hold. That means if it does not hold, what happens? F of p, then f of p greater than some f of x. F of p is the supremum. At the same time, f of p is different from the supremum, or there will be some points which having inequality. That means not equal to result. There will be some point in such a way that f of p not equal to of f of x. That is f of p greater than the supremum f of x, or f of p greater than f of x, or less than x. There will be result with the not equal to. Okay. So then consider m is the supremum. We are considering m is equal to supremum of x belongs to D. There will be supremum because we have already shown that it is bounded. F of x is bounded. So we have already shown that it has supremum and infimum. So let us denote capital M is equal to supremum of f of x. So what is the specialty of supremum? Supremum will be the highest point or maximum point. So m minus f of x will be greater than 0 always, because all other f of x will be below capital M. So m minus f of x will be greater than 0 for every x belongs to D. So that is a positive value. M minus is a positive value. Consequently, the reciprocal of the positive value is also again positive value. So 1 by m minus f of x is also positive. Moreover, we have f of x is continuous. That is the preliminary assumption in the theorem. So since f of x is continuous, m minus f of x is continuous, and hence 1 divided by m minus f of x is continuous. So we can say that m minus f of x raised to minus 1 is positive and continuous in D. So from the above paragraph, we have showed that for a continuous function defined over the closed bounded interval is also bounded. So we know that m minus f of x raised to minus 1 is a continuous function, which is also defined in the closed bounded interval D, and hence it should be bounded. So it is bounded by the first part of the proof. So you know that since it is a M is a supremum, I will show you by plotting. Okay, just look in this figure. Suppose this is the set. Okay, this is the suppose this is a set. What is a supremum? Supremum will be this point. Okay. This line shows f of x values. Okay, in the univariate case. Suppose we subtract a positive number from m. Where will be the position? Yeah, position will be somewhere here. This will be m minus d or delta. Okay, this is the position of m minus delta. So there is an interval where the interval consists of some f of x values. Okay, so if we subtract a positive number, we can find an interval, and in that interval we will have many values of f of x. So we shall take some what is that? We can find an x delta in such a way that f of x delta belongs to that interval. Okay, f of x d x delta is in between m minus d and m. That is the idea. Okay. So here, however, if delta is greater than 0 is any positive number, then by definition of m, we can find a point x delta in D for which f of x delta greater than m minus delta. Clearly in this picture you can see that f of x delta is after m minus d and before m. So f of x delta is greater than m minus delta. Or we take m in the left side or subtract m, or we can move fx to right side and delta to left side and take the reciprocal. That means we can rearrange this expression and we get 1 by m minus f of x delta is greater than 1 by delta, because we will, after first simplification, we will get delta greater than m minus f of x delta, and if we take reciprocal, we get 1 by m minus f of x delta greater than 1 by delta. This implies that what happens? This implies that 1 by m minus f of x is not bounded because it is greater than 1 by delta. Okay, it is greater than 1 by delta. If it is less than or equal to 1 by delta, we can say that it is bounded. Since it is greater than 1 by delta, we can say that it is not bounded. So it is a contradiction. So what will be the reason of this contradiction? Our assumption will be wrong. That may be the reason for getting contradiction. So what is our assumption? Our assumption is not, and what is that? For f of p greater than that means f of p greater than supremum of f of x, or f of p less than supremum of f of x. Okay, we are not assuming that f of p equal to supremum of f of x. We are assuming that f of p not equal to supremum of f of x. So this assumption is not equal to assumption is wrong. So for that assumption we got a contradiction. So what the reason of contradiction is that we assume that f of p not equal to supremum of f of x. So we must take that there exists a p such that f of p equal to supremum of f of x. Okay, there exists a p such that f of p equal to supremum of f of x. Okay, that is idea. So I think you got the idea of this theorem. And similar proof can be employed for the case of in Theorem. Okay. I shall check when you submit that results in your notebook through Moodle. Anyway, you may read and understand, try to understand and write in your notebook. We have one more theorem that is we will discuss today itself. Second theorem. Suppose that D is closed and bounded. The context is same. Suppose that D is closed and bounded set in Rn.